confusing. Hang on. Oh, hang on. Good morning, everybody. Welcome to our special interest group event for design simulation and metrology on disruptive and future innovations. My name is Pim van Baarsen. I'm CEO for the Silverstone Technology Cluster. I'm not actually going to be hosting the event today. We have Rob Rousel with us from Worth Research, who is one of our champions for this particular group. And Rob will run us through the day and lead proceedings. So I'm just here to sort of welcome everybody and a little bit of housekeeping. You should see on the right-hand side of the screen, there's a panel there for where you can ask questions. You should also have the ability to raise your hand, which I think is at the bottom of the screen. And if you do that, we can invite you on the screen, so or onto the stage, so you can ask your question in person if that's what you want to do. So do please use the chat functionality. Please use the question functionality for all your questions, and Rob will address these, or indeed raise your hand. And hopefully you've all already enjoyed the networking session, and we should have a networking break in the middle, and then sort of a bit more networking towards the end as well. So that's kind of it from a housekeeping point of view. So I shall now hand over to Rob to run us through the day. Thank you.
Thank you very much, Pim. Welcome to this event from the DSM SIG. I don't know if many of you know what the DSM group is. It's the Design, Simulation and Metrology group. We focus on the digital workflow from, say, laser scanning something and reverse engineering it, designing it in CAD, taking it through simulations, whether it's FE or CFD, and eventually going on to manufacture with digital methods to aid manufacture, and then maybe metrology again to sign it off. This event is about horizontal innovation or disruptive technologies, which is really interesting to me because I'm from a company called Worth Research. We've got a motorsport background where we used to design race cars, and we've evolved and morphed out of motorsport into other industries. So we now use particularly our computational fluid dynamics and aerodynamics expertise that was honed in motorsport, and using it as a disruptive technology in other industries that haven't had that access to that level of aerodynamics. And we focus on trying to make systems more sustainable and save energy. So rather than in the old days, we would be making a race car go faster and faster for a given amount of fuel, we now make systems perform as well, but for far less fuel or far less electricity. So that's me and that's us. And first I'd like to introduce Taff from the Open University. Some have said he's the greatest inventor of our generation, and he's an innovator and an entrepreneur. So if Pim launches Taff onto the stage, that would be great. There we go. Thank you, Taff. I'll just hide myself.
Good morning, everybody, and thank you for attending. And thank you for such an amazing introduction. I'm a bit more modest than that, I think, but hopefully what I'll get across today is some of the work we've been doing at the Open University and with some of my startup companies to try and develop innovations and research into the benefits of sniffing species, whether that be in space or back here on Earth. And so today, in the next 20 minutes or so, I'll take you on a bit of a journey that's 25 years in the making, covers about 4 billion miles around our solar system, before coming back here and hopefully give you an example of how we can start to address some of the challenges back here on Earth. So I'll just share my presentation. Share screen. Can you now see that? Can you all see that? Okay. So, as I mentioned before, the talk is about innovations and how we apply sniffing methods to determine and the analytical questions and turn those into products or services for end users. So I'll start with the space research. I've been lucky enough to be involved with 2 space missions. The first one was the Rosetta mission, which chased a comet. And after 10 years and 4 billion miles, we actually landed on the comet and analyzed the chemical composition. So comets, when they fly past the Earth, are some of the largest structures in the solar system. So this picture here from the Southern Observatory shows you the tail of a comet. And of course, the most famous one that comes around every 80 or so years is, of course, Halley's Comet. But in reality, the nucleus of the comet is much smaller. And the comet that we went to is called Churyov-Gerasimenko, after the Ukrainian astronomers who discovered it in 1969. And that comet is only about 4 kilometers across. So if you're to overlay this with London, it would stretch from Big Ben to the Tower of London. The other thing you can see is it's quite a funny shape. We initially kind of modeled the comet and being the shape of a potato, but in reality, it turned out to be more like a rubber duck. So it had a big body and a smaller kind of head. This is a picture of the comet itself, taken a month before we landed. So this is in October 2014, and it's probably the world's most expensive selfie. So it's a picture taken by a camera on the lander, looking across towards the comet and also the solar panels on the actual Rosetta orbiter. This also has one of the oldest and one of the youngest things in our solar system. So we go to comets basically because they're left over from the beginning of the solar system. It's where most of the light elements are found. So things like water, carbon monoxide, carbon dioxide, methane, nitrogen. And the purpose of the mission was to go and see if the building blocks of life are present on a comet. So the other thing was to look for the water and the isotopic signature of the water to try and understand if comets could have brought A, water, and B, the building blocks of life to Earth early on in Earth's history, because there's a lot more water on Earth than might be expected from geology. This is the instrument we built. We shrunk something the size of a family car down to something the size of a shoebox, and it was called Ptolemy. It's a miniature gas chromatograph isotope ratio mass spec, and it allowed us to separate and then also analyze the chemical composition of the comet. You can see here we've had a couple of very prestigious articles, including in Science magazine, where we were able to confirm that the building blocks of life, so molecules containing complex organic compounds, carbon, hydrogen, oxygen molecules, were present. And that's because it probably formed from UV interactions with gases such as methane or water or carbon monoxide, carbon dioxide, and that allows the buildup of these long chain kind of organic molecules. The picture on the bottom right hand side is to show that we were the very first thing that went on the lander. And this picture is from September of 2001. We launched in 2004, and we actually got the data back in November of 2014. So the thing about building space instruments is you need to make them small, light, robust, low energy, low power, but also be able to fit within the constraints of the mission. So that includes making sure that it can survive extremes of temperature, radiation, and also, of course, working in a vacuum. So a lot of design goes into these systems. It builds up on previous heritage, but there also is a need to innovate and develop new solutions to challenges. And to do that, you need a multi-skilled team. And once you have that, then you have quite a strong capability for future challenges, whether that be on Earth or in space. So my colleague, this is a picture of the ion trap mass spec that we developed. So again, these electrodes would normally be 4 or 5 kilograms. You can see that here the electrodes were machined down so that it still does the physics and the engineering, but you actually have taken away all the excess mass. And so we shrunk this down to something that weighed just over 50 grams. In terms of power, mass specs normally use a filament, which we had to remove, and we now use so-called field emission nanotips, which allow you to generate the electrons to ionize your gas, but it does it for significantly lower power. So you can, as you can see there, we use less than 1 watt. So as I say, this requires a big team of people with multidisciplinary skills. So we have engineers, we have physicists, we have chemists, we have microbiologists in certain projects, geologists. And again, as I said, that makes a very strong team which can look at several challenges. Just to make you aware that we are still involved in space science, and my colleague Simeon Barber is leading something called Prosper, along with Simon Sheridan, who has a separate project. But these are looking at how the moon can be used as effectively a petrol station on the way to the rest of the solar system. So you've probably heard about Elon Musk going to Mars, and Jeff Bezos wants to put Apple manufacturing on the moon. Now, if you're going to do that, you're going to need to find resources in situ. So the in situ resource utilization demonstration is ongoing. And one of the first things to look for that will be a Russian-led mission. And we're providing the European capability to allow it to sniff the south pole of the moon to look for the presence of water and other volatiles. If those are there, then of course you can then process, or capture, and then process the water. You can use that to split it to form hydrogen and oxygen. The oxygen, of course, can be used to maintain the life of astronauts. You can, similarly, water would be used for the astronauts. But you can also combine hydrogen and oxygen again to form rocket fuel. And the gravitational well on the moon is significantly lower than that on Earth. And so it provides you, as I say, with a potential pit stop on the way to the rest of the solar system. And that could include doing things like asteroid mining as well. So you might be thinking, okay, that's all very well, that's space. That's, it's good to know these things about comets and what have you, but so what? What has space ever done for you? And actually, if you go to Australia, one of the things you'll find out when you go on a tourist bus is that one of the biggest inventions that we all use every day is Wi-Fi. And Wi-Fi was actually invented by radio, or the process of Wi-Fi was actually invented by radio astronomers from Australia. And it was to solve the problem of signals being, if you send a single signal, it obviously will collide with things on the way and you can disrupt that signal. But if you send a signal in several beams, then that can actually be used to prevent this and maintain the majority of the signal. And this was invented way back, I think, in 2000, in the early 1990s, patented in 1996, and they won a large court battle with all the kind of technology manufacturers in the mid, I think it was 2015-16, which meant that all those companies have had to pay royalties back to these radio astronomers. What I'm hopefully going to show you next is a video which will show you how the European Space Agency has developed other technologies that can be used back here on Earth. So as you can see, ESA have a very proactive program to try and translate space know-how to things back here on Earth. I'm always amazed when I watch that video why someone would need fireproof underpants. Apparently it's for the steel industry. And in the middle there, you saw two applications. One was bed bugs and the other one was submarines. And both of those were projects that I've led. And so back in 2009-10, we were approached by BAE Systems, who manufacture UK submarines, because of our work on Ptolemy, to we were asked to develop a new air monitoring system that can be used on board all future UK Navy submarines. In the middle there, you can see the system we developed, and it allowed BAE to make the decision that says that they can stop using currently American-based systems. So we've broken a 30-year monopoly on that. The system is faster, better, cheaper. And most importantly, it's now going to be manufactured by a UK company called Analox, which means for the first time in 30 years, the UK has a capability to monitor the air quality on board submarines. It has a redundancy because we can now put more of these systems on board the submarines than previously, making it a safer working environment. Submarines are important to the UK because they provide us with the strategic defence capability and have done so for the last 50 years. We have 4 submarines that provide that capability, and one of them is always at sea. So to have a fully working system that can be maintained is really important. And these should be going in service, hopefully this year, on board the latest system called the Astute class. We have generated, I think, over a dozen jobs in Analox, and it has changed their business model for the next 50 years. Other sector disruptive technologies we've developed include a miniature robotics system that can also do analysis. And we've developed this for Geraint, who are the world's largest fizz and fragrance company. And they produce a quarter of all the perfumes that get used in a range of household items, such as shampoos, toothpaste, washing powders, up to high expensive perfume. And this is a good example of how we have taken technology out of the university through to our company to then deliver to a large multinational. And this system is primarily being used to look at how they can change the formulations to remove microplastics from their products. So potentially quite a big environmental shift. And also this is an enabling tool to allow them to do that kind of changing processes. We've also developed in partnership with the Scotch Whisky Research Institute and also IBM Research, or rather we're in the process of developing a fully automated assay to allow Scotch Whisky Research Institute to detect counterfeit and adulterated Scotch whisky. Scotch whisky is one of the biggest net contributors to the UK economy, and it's all based on brand. So anything that can damage the brand is obviously bad news. And so the SWRI work for the Scotch Whisky Association, which is the trade association for the sector, to ensure and remove products that might be damaging the brand. And so we are using IBM, using AI or machine learning to take our data files to then turn those into basically screening tools which can be used to identify problem whiskies. You may have seen last Friday the government announced a £210 million programme with IBM at STFC Hartree to develop AI and machine learning algorithms for UK industry. We've had a whole range of other projects funded through something called Sprint. So Sprint is led by the University of Leicester with the 5 other major space universities, including the OU. And Sprint is a funding program that allows SMEs to bring challenges to Sprint with a view to it then funding projects which can then deliver impact. So as you can see, the Scotch whisky work was initially funded by Sprint. We're working with flavour companies. We're helping companies develop new products. For instance, we're doing some work on developing of a new oak-aged brandy with efficiency technologies, as well as working with them to develop new tools for the craft beer and distilled spirits sector. We also are looking at how we can turn food waste into food supplements with Nutripharma. Laco, our instrument manufacturer, and in fact, we've just signed a 5-year deal with them or in the process of signing a 5-year deal, I should say, to have a strategic partnership to help develop a whole range of new analytical processes using their instrumentation. And Tissix is a gas tank manufacturer, and we're helping them scale up their processes by automating their kind of production processes using sniffing methods. I'm also pretty active in food and how we can help detect issues with food through sniffing, whether that's avocados, determining the shelf life of bagged salads, or even looking for food poisoning. Oh, the bacteria that causes the primary cause of food poisoning in the UK, and that's to do with chickens. So we've developed a method where you can look for the signature of the bacteria just by sniffing the air within a chicken shed, which then allows you to process and intervene and hopefully reduce the issues for people down the line. We also work in health, and again, we can mimic dogs, and using artificial intelligence or machine learning, we can learn the profile of cancer. We can look at sports testing to hopefully prevent people cheating in the future. And we've even helped develop the protocols by which the NIHR or MHRA rather would use to evaluate the performance should someone develop a rapid breath test for COVID. So I've helped as a consultant, along with many others, develop that kind of program, which would say, okay, this is how well it would need to perform. And again, if this was developed, and certainly it would help us in opening up events and have people tested in real time with results in less than a minute, rather than the kind of timescales currently employed. As Pim mentioned, we've developed a valve technology which is derived from Rosetta, but was sufficiently different that we actually managed to patent it back in 2009. I'm working with my colleague Simon Sheridan and also Charles Opoku, who's an STFC Innovation Fellow, to look at how we might apply this both in space, but also in the hydrogen economy, and the drive towards the net carbon zero by 2050. My company, Applied Science and Technology Solutions, has a manufacturing license, but we also have other projects, like we work with AVS, who are a Spanish propulsion manufacturer, to explore how that might be used in space. And in fact, we are currently in negotiation about the possibility of them licensing the technology for that. But the other big area, as I mentioned, is beyond space, and also that's in the hydrogen economy. Increasingly, it's looking like we're going to have to use, whilst batteries may be okay for cars, they're not going to have the energy density for larger vehicles like lorries and trains. And so we're in discussions with several companies currently, and this just gives you the idea of the landscape of the companies we're talking to. And as I say, we're hoping to be able to license or even sell this technology to the various stakeholders. So we're also involved in policy, automotive, alternative hydrogen sources, the satellite propulsion. We have NDAs with over half a dozen companies all interested in this capability. And where the valve comes in is it has no plastics or rubbers in the wetted parts. It has a very, very low leak rate, also been having quite a high flow rate. So it has all the kind of characteristics that overcome some of the problems that they have in the hydrogen sector currently. But this is very much a growing sector and very young currently, and so we're in, as you can see, we're in discussions with a number of people who are leading that work already. In terms of commercialization, I have 4 companies, one of which has Oxford Micromedical has the offer of a very large investment, although we're just waiting for the money to transfer. I have another company that is looking at bed bugs, but that's currently dormant. And applied science and technology, you've already seen already with Geraint and also the other project with the valves. So Oxford Micromedical is taking the know-how and lessons learned from Beagle 2, and the technology applied there can also be applied to a medical process, which is the urea breath test. So this is the primary cause of stomach ulcers and stomach cancers, particularly in places like India. But as you can see, this is all about engineering and building basically a tool that can be affordable. So one of the areas we are looking to go forward is to partner with people who can provide us with these, well, basically the parts, the component parts. So again, you know, the thing we recognize from working in space is that you can't do everything yourself. And so you need to partner with people. And so just to summarize, we have a track record of delivering sector disruptive solutions. We have great analytical capabilities at the university to allow us to look at a number of different samples. So if you have challenges, perhaps we can help you. And as I say, we work in partnership with end users, manufacturers, but also delivery partners to develop these solutions, and hopefully with impact, with reach and significance. So just to finish with the final slide, who we were looking to work with, well, pretty much anybody in engineering. It's the one area we don't have within our team significant expertise in. So we're looking to work with people who can provide us with CAD/CAM, CNC, machining, additive manufacturing, stress strain modeling, computational fluid dynamics, but also how we take our kind of, let's say, software and electronics that work, but how we turn those into commercial solutions that can be produced and sold as a product. Now that's not an exhaustive list, so if you have any ideas, why don't you come and join us? And my email is there at the bottom left-hand side. Thank you.
Brilliant. Thank you very much, Kath. That was fascinating. I've got a few questions, but I should probably open it up to everyone else. So does anyone have any questions that they would like to ask? Does everyone know how to ask questions? There's a Q&A bit where you can, in the messages, you can go Q&A and then post in a question. But while people are trying, I've got a couple of questions, but the first one is a little bit open-ended in the space race, how it's changed from over the last 40 years to now. What if you had to do some future gazing to predict what the next 10, 20 years will look like? What kind of prospects excite you the most?
Well, as you say, the whole landscape has changed in the last 10 years or so with Musk's and the Bezoses of the world, you know, although hopefully Jeff will survive his trip in a few weeks' time or a few months' time. Yeah, so that really has kind of shaken up the whole industry. So, and also the other area is in the satellite communications, and the idea that satellites no longer have to be these massive, you know, several ton systems. They can now be as small as 30 centimeters by 10 centimeters, so-called U-cubes. So for us, with the valve technology, that opens up a whole range of opportunities for us. In terms of space exploration, then, you know, we are going to be going to Mars. We are going to be going back to the moon. We are potentially going to have a new international space station which will circle the moon. So we call the Lunar Gateway. So yeah, there's lots and lots of new opportunities, and you know, some of it will depend on the results we get from those missions to the moon, whether or not there are resources there that can be used and open up a whole range of other activities. But yeah, it's a very exciting time, and the good news for the UK is that despite Brexit, our membership of the UK Space Agency is still intact. It's a completely separate arrangement. And so, you know, we will have opportunities to be involved in many missions, hopefully, going forward. I think the other thing that's increasingly happening is the use of satellites for Earth observation and the use of space data by a whole range of new companies to look at simple things like flooding, but also environmental, the deforestation, and a whole range of different kind of applications. And the more satellites we have, the more data we have, and the more people can actually use that data to make strategic and planning decisions, and even do, you know, disaster management or whatever, to be able to, you know, get very good data, very good information now in near real time.
Cool. Has anyone else got any questions? Because I do have one more. I'll go again. You mentioned earlier about electrification and battery cars versus hydrogen. Backstage, I mentioned a quandary I've had over the last few years about not wanting to have a polluting car, but equally not being convinced that battery is the right way to go just yet. And I just wondered if you had any thoughts on that might steer me in the right direction.
Yeah, so having got this valve technology, I've kind of been drawn into some of the discussions around the future capabilities, and we have a professor at the OU, Bill Nuttall, who is an expert in kind of national scale energy kind of movements. And so certainly I think cars are going to be okay for batteries. However, the question becomes one of the national infrastructure, and how do we get the electricity into the right places at the right time? Because everyone will be switching their cars on in the evening probably to charge up during the day. And as it stands, my understanding is we can't, the national infrastructure won't allow that electricity to get into big cities in the kind of levels that's required. And being realistic, as you get bigger and go beyond cars, then there isn't enough energy density in the batteries to allow you to use like lorries and trains. And so they're going to be a hydrogen solution almost certainly. But in reality, the whole, and again, one of the biggest energy drains on the UK is obviously home heating. And so they reckon that, you know, electricity will form part of that, although there's a loss of, you lose energy in transmitting electricity as well as anything else. But they are talking about increasingly ground source heat pumps being used in houses, but also hydrogen being used to replace methane that we currently have in our boiler systems. And a lot of work has already been undergone to change the network to allow hydrogen to be transmitted around the country. So the utility companies are already thinking ahead about how this might be done. But the reality is it's going to be a mixed model, I think. So there'll be renewable energy, of course, and there'll be other sources, but it's going to be electricity, hydrogen, and renewable sources.
Brilliant, thank you. I don't think there's, So Jeremy has asked, we'll have two more questions, we're a little bit behind, but Jeremy Howard Knight has asked whether you mentioned the use of sniffing driven by AI algorithms for various applications. Could the same techniques be used to develop a sniffing technique for breath tests for COVID?
Yes and no. The problem with the techniques that I use is that the analysis takes probably 20 to 30 minutes from sample, which is then not within scope of where they'd like the testing speed to be for these applications. However, there are different mass spec techniques that do give you answers within a few seconds. And the difficulty there is that, for instance, in our urine samples, there's over 1,000 compounds in the headspace above a urine sample. So it's how you untangle that really complicated background signature and how you pull out the target molecules from there. But I think you're right, it's never going to get done by a human, and so it will need machine learning or AI to try and unpick that very complicated signal.
And thank you very much. One last question. How do you think the supply chain supporting the activity will evolve in the UK? And that's from Philippa Glover from CNC Robotics.
That's for hydrogen, I presume, or?
Yeah. I presume so, yeah.
Yeah, well, yes, it's quite interesting. And there are a number of UK companies who are leading in some of these areas. So, you know, companies like Luxfer are already producing the gas tanks that are used to store hydrogen. So they produced, I believe, the gas tanks that are on the first UK hydrogen train that's currently in operation, as well as providing gas tanks to companies like Hyundai, who developed hydrogen-based lorries. So there will be opportunities for people to get involved in the supply chain. Again, we've done some initial work with the University of Coventry, who have the advanced low carbon propulsion system, and they're working with companies like Jaguar Land Rover on how you test. So they're moving their current capabilities, which are related to petrol and diesel, and how they might modify those to test, you know, the capabilities in engines and supply systems for hydrogen cars. So I think the opportunity is there. And it's up to companies to get involved.
Yeah, more involvement, the more the cost comes down on the whole industry, doesn't it?
Yeah, and I think so. One of the disadvantages of hydrogen currently is the cost per unit of hydrogen when you compare it to oil and gas. But that price is coming down all the time.
Okay. Well, thank you very much, Taff. It's been fascinating, but we've got to move on now. So next up, I'd like to introduce Filomeno Martina, who is going to be talking from WAM 3D. They've been leading research in large-scale metal 3D printing. And he's going to be sharing how they use metrology during the build process to make the building more efficient and therefore cost effective. So thank you very much, Filomeno.
Thanks Rob for the introduction, and thanks to Pim for the invitation. I was really looking forward to this because often the talks that we deliver are mostly about business cases and, you know, showing people how technologies can improve operations or save money. And as a former academic, it's quite nice to go back to topics that are perhaps a little bit more technical, such as the one of metrology. I'm going to share my screen just now. I will assume that you guys can see it okay. If you don't, then please do give me a shout. The talk will go over 20 minutes. It's split, broadly speaking, into 3 areas. The first one is a general introduction to the wire plus arc additive manufacturing technology. The second one will be about case studies, just to give you guys an idea of how you can apply the process to the manufacture of metallic parts. And then the third and last section will be finally on metrology, with a particular emphasis on a new sensor that we have developed at Cranfield that now One3D is commercializing. So by way of an introduction, One3D, first of all, we are a Cranfield University spin-out company. We were established in 2018 after about 15 years of research in the field of large-scale metal 3D printing at Cranfield University. And we are here effectively to enable you guys to implement the WAM process successfully within your organizations. And to do so, we set out to provide all of the necessary tools and the technical solutions that you guys would need to implement the process. In terms of the broad landscape of AM, effectively you require 3 ingredients to have a process that is functioning: a heat source, some feedstock, and a motion system. Heat sources can be laser beams, electron beams, or in our case, indeed, electric arcs. And normally the choice of feedstock is based on whether powder typically is pre-placed on a bed or is blown directly into the heat source, or wire, of course, which can only be fed directly into the heat source as well. And depending on how you combine these, you have a wide range of metal 3D printing processes. Certainly processes like SLM, so powder bed, or electron beam melting are way more established than ours, so the wire and arc AM one. And we hope to catch up in terms of industrialization and deployment of the technology over the next couple of years. It's very important to keep in mind that those technologies are typically a complement to each other. So in our case, as you will see from the case studies, we can't really deliver highly complicated net-shaped structures because we trade that capability off with the scale that we can achieve, the speed at which we can print, and the cost, the resulting lower cost of the manufacture. So it's always a blanket which is a bit too short, and you have to decide whether you cover your head or your feet, so to speak. And so just like that, when you're choosing an AM process, you've got to choose the right one for what your company needs. To show a little video of one of our prototype systems over at Cranfield University, you can see here, effectively we are using anthropomorphic robotic arms. We are fairly agnostic to the make, but it's fair to say we've done way more development with KUKA than with the other ones. Robots are nice, they are flexible, they are scalable, they can be combined, as you can see here, with other robots to have even better scalability or better allocation of duties and tasks. And what they can do, especially if you combine them with trucks, is to enable massive parts to be printed. And what you can see here is a mild steel cantilever beam, which is actually 6 meters in length, that we made within a European project that we closed last year. And just keep the so-called end effector in mind. It is the printing head which is attached to the robot. And as you can see, there is quite a large number of hoses and cables that are coming out from it. Some of them are providing services like gas feed, but the vast majority of them actually houses sensors of various types, as I will show later on. Typically, when a customer or a potential interest party wants to embark on the journey of WAM, the customer journey starts from a quick introduction to WAM. Then there is the idea of developing and building a business case, because at the end of the day, the most important thing we are trying to do is to make operations leaner and metal part making cheaper. Then at that point, you have to convince your metallurgist. Therefore, proof of concepts, mechanical tests are needed. As we often look towards mission critical part, qualification is indeed a fundamental aspect of the journey as well. And then at that point, if everything goes okay, and if we have demonstrated together that the process actually works, you think about entering production, at which point you might need capacity that you can get from bureau services, or you could get your own systems for internal part production, of course supported by training, upskilling, and other types of continued support, such as the provision of consumables. And because of the breadth of the research activities at Cranfield and within the large collaborative research programs over there, we've been able, and we've been lucky actually, to have developed a wide range of complementary processes, products, and services to effectively cover the entirety of the journey. And really, we're very proud of this. It really sets us apart from the competition in our field, because instead of giving only the machine or only the software or indeed only the wire or some consultancy services, what we have tried to do from day one is to be available and have enough talent to be around for the entirety of the journey for a smooth user experience toward the implementation. A brief history of the company, as I said, only 3 years ago we were founded. In December 2019, we had the luck in insight of signing an investment deal with a corporate venture from Singapore. Obviously, unbeknownst to us, only 3 months later, the whole world was going to come to a halt. In a way that enabled us to focus our attention inwards with obviously the setting up of the backend infrastructure that we didn't have at the time as a young, small spin-out company, and of course to crack on with both the recruitment activities and the last few steps of the industrialization of the products. And at this point in time, it's already 25 of us in the company. It will be 30 of us in the next month or so. We've got a wide range of skills and ages, all the way from young apprentices to senior and navigated in industry experts that have joined us to fill those gaps that we have, especially as former academics. So coming on to the second section, that of the case studies, one of the nicest one we've done is this pressure tank for space exploration in titanium 64. Typically, this part would be composed of 3 sub-components, each of them machined effectively from solid blocks of titanium, which are then welded together. In the case of WAM, we started from a rod, we printed the main body and then the ribs on the outside in one go, effectively. As you can see, the process once again is near net shape, which means that a finished machining operation is still very much needed in most cases. But even so, for this component, we were able to save about 200 kilograms of titanium on a part-by-part basis, make it 40% cheaper and 65% quicker to make. Perhaps the highest profile component we've made at Cranfield, actually, with the support of BAE Systems, is this Typhoon Eurofighter rear frame. BAE Systems have been very vocal about the potential that AM in general and WAM in particular in this case can enable them to go from 100 weeks to 100 days for the manufacture of these large metallic structures. And of course, just like in the case of the tank, obviously you can appreciate how mission critical this component is. It connects the 2 engines to the center fuselage, to the vertical stabilizer of Typhoon. And of course, coming on to the third topic later on, that of the metrology, from a quality control, quality assurance, and confidence standpoint, a continuous monitoring and observation of the process is certainly key to predict whether the part will have acceptable or unacceptable or no faults at all at the end of the manufacturing process. That's the part you saw in the video earlier on. What this picture actually wants to show is that, of course, while we know too well that all 3D printing processes will suffer from residual stress issues, especially because at the end of the day, as posh as we might want to make them sound, they are made of miles and miles of weld metal, sorry. In this case, by an innovative way to manage the clamping and the tooling and the fixturing during the manufacture of the part, despite the enormous length of the component, again 6 meters, after unclamping and prior to any stress relieving heat treatment, the part was pretty much perfectly flat. Flanges for oil and gas are becoming our bread and butter. Actually, we have done quite a number of these for a number of partners, both academics and industrial. You can see the part as deposited, still in fact on one of the systems, and then after being machined on a lathe. Industrial gas turbine blade, just another interesting example of how we can somehow explore the freeform capability of the process with these twisted structures, and also the flexibility of robotic arms in combination with the 2-axis servo positioner, because effectively the part was reorientated during the manufacture to enable the printing of those overhanging structures at the bottom prior to the main aerofoil being printed in a second stage. In terms of material portfolio, a long list of titanium alloys, aluminum alloys, and steel. So obviously aerospace, defense, space, and oil and gas energy being the prime industry sector to whom we talk. Refractory metals, extremely challenging to work with, but certainly very exciting in terms of their potential, especially in the context of extremely exciting applications such as nuclear fusion reactors. And then again, Inconel for oil and gas, and then a few more alloys such as copper, magnesium, Invar, or bronze. And to a certain extent, the bottom line here is that if there is welding wire available, then most likely we can print with it with success. Despite our short life, our young age, we are very proud and we feel very blessed to work with a number of very exciting and large organizations. You guys were mentioning SpaceX and Blue Origin just before. We are one of the premium suppliers to Relativity Space, whose business model and vision is to print entire rockets in less than 60 days. And that of course, is going to be fairly revolutionary. Avio Aero in Italy, Airbus Defence and Space, a number of other organizations in industry, but also, as you can see at the bottom line, also academic partners such as Cranfield, MRC, Strathclyde, and even a university in Rio in Brazil, which we were all looking forward to visit to have a bit of fun on the beach. But as you know, COVID unfortunately got in the way. So finally, and hopefully the most exciting part of the talk about why metrology is important in AM in general. I'm going to start from there, and then in particular in the case of wire and arc additive manufacturing. So first of all, it's very important to underline a very, very crucial difference between more established ways of producing metallic parts, for example, subtractive manufacturing, or both in the case of machining from forging or from billets, and that of the additive case. So in the former case, it's fair to say that pretty much the properties are available to us already in the raw material. They are somehow locked in the raw material. You buy a billet, you buy a forged bit of metal, and it comes with a certificate from the supplier telling you, you've got this microstructure, you will have these mechanical properties. And okay, within reason, when you start removing material, if you do it properly, you will not see those properties changing. And so there is a fairly high level of confidence within your operations that the part, when leaves your shop floor, will still have the same integrity, the same mechanical behavior as when it came into your workshop. In additive, instead, the situation is very different and certainly more challenging, because one of the beauties, if you are a fancy material scientist in a way, but also one of the curses of AM, certainly, is that you are creating the geometry of the part and its microstructure, and therefore its mechanical properties at the same time. You have metal powder or wire that is pretty much melted, or certainly taken above critical temperatures, where you start modifying microstructures in a dramatic way. And therefore, what you have at the end certainly does not look like the microstructure or those characteristics that the feedstock had to begin with. And so when we look at the connection between the areas of geometry, your process parameters, as well as the way you deliver your process parameters, i.e. your build strategy, all of these play a role because of thermal effects, cooling rates, reheating areas, in the way they yield your final properties. And so, in other words, you might have two objects that look exactly the same, but because maybe the build strategy was different in one case, or maybe your incoming powder was different in your case, or maybe something happened in terms of the laser calibration or the focal distance shift and so on, your resulting internal properties can be sometimes quite different. And so, whilst on the one hand, sensors are always important to give us confidence in the manufacturing process, in AM, perhaps it's fair to say that they are even more important than in other manufacturing approaches. In our case, typically the kind of variables we would look to monitor are fairly similar to the ones that you would monitor in an old school welding process. So things like the voltage, the current, the wire feed speed. In our case, we also like to monitor continuously the position of the wire, so where the wire is coming into the electric arc that we generate to melt it. And of course, then things get more challenging when you start looking at temperature monitoring because of change in emissivity, interference with the arc light. And ideally, you want to be able to do that before you print, so ahead of the point of deposition, as well as after the point of deposition. And in fact, arguably, the cooling rate is one of the most critical factors to consider when predicting microstructure. So in an ideal world, you would like to have a few more pyrometers in the back of the melt pool to try and capture that cooling rate and predict the resulting microstructure and mechanical properties. For reactive materials like titanium, or even the more exotic ones like the refractory ones or stainless steels, monitoring of the oxygen in the atmosphere is also quite critical. And then, of course, gas flow to make sure that you don't have any deviation, which can be dramatic in terms of effect on the melt pool, but also in terms of cost. But perhaps the most challenging and, to a certain extent, most critical variable to monitor is the layer height. And here we have to make a clear distinction between the way the layer height behaves in powder bed, where the bed is pre-placed, the laser scans the bed itself, and then once that layer is completed from a scanning point of view, the whole platform is lowered by a fixed amount, and a new layer of powder is brought up onto the previous one. And of course, in this case, arguably there will be always deviations, but in general, the layer height is identical to the step at which the platform moves downwards. And so, to a certain extent, achieving the right geometry in powder bed is certainly easier than our case, in which, as you can see on the right-hand side, effectively what we are doing is microcasting in free space. There is no mold to control the shape at which the molten material will solidify. And there is a number of much larger thermal effects to be taken into account. So obviously, if you take a step back in terms of preparing your machine on the digital workflow, you have got your CAD file of the component, you have to do your slicing, you have to program the trajectory of the motion system, and then you have to populate that trajectory with your process parameters, how you set the metaphorical, the resulting layer height, and indeed the geometry in general, as well as the integrity of the part you are printing, matches the one that you did your slicing at in the digital environment. And so with this in mind, then of course, it would be helpful if there was a method to continuously monitor the layer height as the main proxy to assess that the correct geometry is being deposited. And commercial systems are based typically on contact or contactless methods. I think all of us are familiar with the laser scanners. So you print your structure, you stop, and then you come with a laser scanner, you use lights to measure the shape, you reconstruct the shape, and then of course you can compare with the intended or expected outcome. And then of course, whilst this is somehow an established technique that can be used somehow easily, it has the drawback of increasing the non-printing time of the machine, which arguably is also non-value adding time. And in the context of utilizing machines to the highest extent and reduce cost further, obviously you want to be printing as often, as highly with utilization as you possibly could. Then there is other approaches based on CMM, so with a probe that touches the part, and in that case, the drawbacks would be very much the same. So what we've been trying to do at Cranfield is to avoid those issues and to develop interferometric techniques. The advantage of that is that obviously being interferometric, they are insensitive to the radiation of the arc or the lasers, if you use a laser as a heat source, and therefore they can be done really online. And what we've got to house the sensors, as I said, is our printing head, in which you can see the wire feeding and the automatic wire positioning, local shielding for optional protection of reactive material. Those sensors, which I'm about to talk in a second, to measure the 3D shape and the layer height in real time, and then pre and post deposition temperature with process camera, voltage, and current. So the printing head effectively, it prints, but it also makes sure that everything is going smoothly. We have already sold a number of these units, and it will be featured as part of our catalog system that we are about to announce in the next quarter of 2021. So coming on to the specifics of the sensors, so the what we call coherent range resolved interferometer, or CORI for short. Without going into the details, effectively what it does is, by having a clever data processing software with electronics and a laser generator combined and coupled with a fiber, it enables us to measure the distance between the tip of the delivery fiber itself and the object which the laser is sitting, coming out of the fiber once again. So as you can see in a very basic setup where we have an old school MIG torch with the sensor attached on its back, it's a fairly compact sensor. And again, because it's interferometric, it is completely insensitive to the radiation of the arc, which means that potentially by either comparing the measured distance with one of the previous layer, or as we do in the case of the end effector, by having one fiber in the front and one fiber in the back, at any point in time while the process is printing, we can continuously monitor the layer height that we are achieving. And in fact, if we then take that to the following step, by combining the fiber with gobbo scanners, which enable us to scan the laser beam rather quickly and very precisely at the point of delivering the laser, not only we can extract the layer height, but effectively we can reconstruct the actual 3D shape in real time, which for us, it's an absolutely groundbreaking result, because obviously you can imagine that we're making parts that are of several meters in size, where a lot of things can go wrong for a number of reasons. And the flexibility and the ergonomic of having the geometry continuously monitored is absolutely great in terms of understanding no distortion, no residual stress. Yes, the layer height is correct. Yes, the geometry is correct. To a certain extent, this can be used also to inform downstream processes like machining, because if you have got to do a finished machining pass, it would be nice to have a reconstructed incoming shape so that you know exactly how to set up the part on the machine tool and how to do the machining. Because also you have to keep in mind that to minimize the cost of these components, we always try to have 1 to 3 millimeters max in terms of machining stock. And so it's absolutely great to know exactly how to set up the part on the machine tool. Crucially, this type of measurement technology can be applied to other manufacturing processes. So if you want to try it out on within your own specific application, do get in touch with us and we can discuss the provision of a unit as a standalone device. Then how we bring this all together in terms of quality control is via our WAM control software. On the left-hand side, you can see a number of sensors being displayed to the supervisor of the machine in real time, with bands for alarms and audio signals to call the supervisor attention. And of course, what you can see here is for example, the layer height measured in real time. And then on the right-hand side, you've got effectively a digital twin of the part where you can plot various channels, voltage, current, warp speed, and so on. And then from remote, from away, in true Industry 4.0 spirit, you can see at what stage you are of the printing of the part. So again, to recap the benefits of this integrated metrology approach, well, first of all, we've got a flexible supervisor dashboard. We can record the process continuously and have effectively a part pedigree with a quality data that has been stored throughout the manufacturing of the part. We can automate pre and post deposition operation. And then, of course, as I said, you can access it remotely, make it part of your ERP system, and inform downstream processes on the state of completion of your part. And again, what we do is to sell the software and the hardware very much as part of the one solution. So what you saw just now was just a sneaky preview of what we're about to announce in a couple of months. So in summary, Cranfield have been able to demonstrate that WAM really has the capability to change the face of manufacturing, and I am certainly a very firm believer of that. WAM3D has been established to create a supply chain for the process, We've been really busy establishing a great team full of talent and building up our operational base. And we look very much forward to helping you guys, not just a member of the STC, but also a number of other companies in the UK space, if you think that wire-based AM can make your business better. Thank you very much.
Thank you very much, Filomeno. That was fascinating. If anyone's got any questions, can you quickly post them? I kept coming up with questions, and then you kept answering them while you were talking. So, so Sarah Penrose, what are your limitations on size for tanks from your current capabilities as a business, and are there limitations from a technological point of view and its resulting mechanical properties? Would there be a crossover point with cost efficiencies? And I'll just add one more, because I was going to ask what was the driver for the weight saving on the tank one you did. So answer Sarah's stuff first, and then
I'm going to start actually from your question, because it ties in with the cost efficiency point. So in the case of the tank for water containment, there was no actual weight saving. The final geometry was identical to the traditional one, except we were able to save all of the material that would have been otherwise machined. So normally when we look at a cost comparison, the main proxy is what we call buy to fly. It's a ratio which tells us, okay, you've got to buy 60 kilograms of material for every 1 kilogram that, for example, ends up flying. And in the case of that tank, that ratio was something like 45. So typically for a buy to fly of 5 or above in titanium, because obviously it's a bit dependent on the material, we start seeing a cost saving. Obviously, the higher the manufacturing waste today, the better the chance of saving money, time, and improve environmental performances. In terms of the size, it very much depends on the regulator, because obviously the part for Typhoon, which was quite big, was built using local shielding solution. So it was built in an open environment with no inert atmosphere provided globally, but with local inert atmosphere created by our inert end effector. And unfortunately, today, there is no regulatory framework that would enable you to put that thing on an aircraft, but things will change because it's a matter of statistical confidence. The catalog product that we're about to announce, the new machine, has a building envelope of 2 meters by 2 meters by 1.9. So that is fully enclosed within a, again, enclosed volume that can be filled with the argon inert gas. So if your tank in stainless or titanium fits within that volume, then chances are we can build it. And then if it doesn't, we can always recur to the local shielding methods, but then it can be a bit complicated to convince the authority that such a new approach can be feasible straight away.
Thank you very much. And we've got a question from Jeremy. Very interesting tech. Any thoughts on adding the remaining 2 axes?
I'm not sure what Jeremy means by adding. So at the moment, we've got the 6-axis robot on the top, and then we have the 2-axis servo rotator at the bottom. So effectively, we can move the part relative to the torch, but also the torch relative to the part. So in welding, it is known that you can weld around the circumference of a pipe, for example, also against gravity. So when we've got to do overhangs, we can do that with the torch horizontal, for example, or by reorientating the part continuously. We can also use the rotator in combination with a tailstock to build symmetrical structure, which can be quite beneficial when it comes to managing bending type of distortion. So again, do we really need 8 axes? I don't think so. If we had a 5-axis CNC motion system, we would be able to build the same geometry with the same complexity. But again, the flexibility that we have got from the robotic arms and the tailstock and the rotator is certainly great.
Brilliant. And I've got one more. I noticed a lot of interesting industries you're starting to work with, and I was immediately starting to try and think of other applications. And one industry we do quite a bit of work with is architecture, and I was wondering whether this kind of thing could help weight saving on steel structures or what have you?
Yeah, absolutely. So in terms of marketing urgency, we see architecture as a kind of phase 2 field for us. But there will be benefits. The cantilever beam that you saw in the video was designed by Foster and Partners, one of the most technologically savvy architectural firm with whom we collaborate very closely. And actually, I don't mind pointing you guys towards our competition. If you check out a company called MX3D in the Netherlands, they've printed a 6 meters or 7 meters long bridge that they're going to put in the red light district in Amsterdam at some point in the near future. So if you're looking for an actual excuse to go to Amsterdam and visit the red light district, I think it can't be any better than that. And they've also printed a number of nodal connections with the view of avoiding fabrication of connections that when you're doing these complicated shapes are fairly unique and one-offs. Of course, if you can print them straight from CAD, you can leverage the benefit of the digital aspect of AM fully and reduce weight as well. So whilst we're focused on a lot of old school, maybe boring applications like wing spar, wing ribs, landing gear ribs, MX3D have gone full on with the lattices and the freeform aspects. So do check them out because they've been doing a great work.
Cool, brilliant. Thank you very much for that. Thank you. I think that was that's it for that talk. Next up, we've got Tim Gears from Hexagon. Talking about
Rob, sorry, one more point. I am due to present and teach in literally 10 minutes somewhere else. So unfortunately, I've got to check out. I will send my deck to Jackie, and then if you guys want to get in touch with me, give me a shout via email, and we can pick it up offline. Thank you very much for the invitation again.
Thank you very much, Filomeno. And good morning, Tim. Over to you.
Hi, Rob. Hi, Rob. Can you hear me okay?
We can hear you clear and loud.
Oh, that's good. That's good. Always a worry of mine when you go online. So let me see if I can click on the right screen here.
Okay. Yep, it's working.
Okay, choose the application. So you can see that, Rob, yeah? Okay, brilliant. Okay, let me just. Okay, I'm working on a dual screen, so it's. I see a blank screen in front of me where the presentation should be. So my eyesight will be a little bit to the right hand side. So apologies all. But I just wanted to say to thank you to everybody, to Jackie, to Pim and the team, and also to yourself, Rob, for hosting this event. It's always an interesting one. When I saw the theme around disruptive and future innovations, it's always quite interesting, especially for a company like Hexagon. So after the two presentations I've just seen, I'm now wishing I went a little bit more technical. To be fair, I was initially, and then I brought it up a level. But I just thought the last two presentations were fascinating. So thank you for them. So let me just go to the screen here. So just a quick introduction on who I am and who Hexagon are, if that is okay. My name is Tim Gears. I'm the business development manager for Hexagon Metrology, and I oversee, I would say, pretty much most of our UK technical partnerships. And a big part of them technical partnerships are the high value manufacturing catapults, where we're a member of 4 of them currently as tier 1 members. Additionally, I support our sales team, because at the end of the day, we're a company that sell, and that is our core. If we don't sell, we wouldn't have a company. I support the sales team directly with I don't like using the word key accounts or major accounts, but I like to call them strategic accounts, really, and the relationships within them that are required from time to time throughout the business. I have over 30 years working in UK manufacturing and also working in metrology. The first 10 of them were spent in automotive as a toolmaker by trade, apprentice, and then moving into metrology. And I put in brackets there what metrology is, because it still shocks me today, the lack of understanding of what actually metrology means when you talk about it. I joined Airbus in 2001, where I worked at Airbus for nearly 7 years. And then I joined Hexagon, which was Hexagon Metrology Limited. But there was a company there called Leica Geosystems that I joined at the time, going back to 2007, where I worked in large volume metrology, but in the portable division. I spent 4 years as an application engineer. Then I've had various roles where now I currently sit in the business development team. I'm very proud to do so. So Hexagon at a glance, and I do think this is important. And apologies if that has been explained to you before by previous presentations on who Hexagon are. But I'm a big believer in collaboration and partnership and working together. And that is why we joined the Silverson Technology Cluster, to work with other members and to help support them. But who are Hexagon? Well, we're a 500 million company when we started off in the year 2000, nearly 20 years ago. And now we've grown to nearly a 4 billion company with 21,000 employees spread across basically 50 countries. But Hexagon, the actual group, are made up of a lot of smaller companies as well, us being one of them, but with over 300 operating companies now. We're a huge believer in R&D and supporting research and development, and you'll see that on the next couple of slides. So you might recognize Hexagon or Hexagon AB pretty much by our brands. And this has been a very hard story to tell on who Hexagon are. If you were to ask a lot of companies in the UK, have you heard of Hexagon? They probably haven't. They might have more over the last, I would say, 4 to 5 years, but they would probably recognize us more by our brands. So Lights, Brown & Sharp, Leica Geosystems, perhaps MSC stands out there, especially with what I've seen so far in terms of these presentations. But our foundation started nearly 20 years ago in metrology. And then as the years tick by, then we moved slightly a little bit, not away from hardware or sensors, but we moved, we added software, applications and manufacturing intelligence into our portfolio. And what I've seen over the last couple of years is an aggressive growth in towards smart manufacturing. So where do I sit? Where does Hexagon sit? We sit within the manufacturing intelligence aspect of the company, which is split really in half. And as part of that, if I go back on there, you've got three pillars, as I call them, or 4 pillars really. The first pillar, which is design and engineering, as part of the manufacturing intelligence. As the second one is production, and the third one is metrology solutions. And something that we have been moving towards, and I'm sorry to use the tag word of digital transformation, but it really is something that we've been working on over the last couple of years, which wraps all them 3 together. So global, how do we touch? So Hexagon Manufacturing Intelligence, we have over 1,500 software developers and engineers spread across the whole world, over 500,000 software licenses installed, and 2 billion worth of sales. That's going back to 2019. And that is spread very equally, you know, in North America, in EMEA, Europe, and also in China as well. But I think this is important to show, because from a local point of view, we are Hexagon Metrology, and we have 94 employees, and half of them employees are out currently in the field supporting best part of 4,000 machines out there currently in the UK. We have a very strong market share of CMMs, so coordinated measurement machines. We have now a 55% market share on portable arms and an 80% share of laser trackers there. And software is something that we've really moved into recently, and we have over 12,500 software users of Hexagon software in the UK. But locally, in the UK. We're a £25 million company. We also have 4 sites, one in Telford, one in Milton Keynes, one in Silverstone, and that is why we're a part of the technology cluster, and another one, Chester. The reason why we're at Chester, we're in Airbus's backyard, basically, in Broughton. So again, I just wanted to touch on this did you know what Hexagon technology touches? 75% of what we touch, of the cars that are produced today in automotive, would have some form of Hexagon technology within them or as part of them. 90% of aircraft and 85% of smartphones. And again, I'm sorry to touch on this again, but design and engineering, production and metrology hardware and software, we're so much more than just a metrology company now. So what is our portfolio? And I know we're talking about disruptive and future innovations, which is why I've put this up here. Now, apologies that I've used like an orange box and a red box, but the red box is our core, is the core assets or the core instruments that we do sell and support. That's laser trackers, that is portable measurement arms, that is CMM, and that's also the software that supports them. That would be PCDMIS, Quindos, Spatial Analyzer. You might have heard a few of these softwares. The boxes that I've put in orange are something that I've really, as a company over the last 2 to 3 years, we've noticed a huge growth in. And that is after sales service, that is automated applications. So if you've got a laser tracker, or if you've got a portable arm, or if you've got a CMM, or if you've got a process, how can we automate that? How can we remove that human element and automate that process to make it as easy as possible? And we've also noticed a huge growth in sensors and retrofit. So a lot of customers are making do with what they've got, especially over the last 12 and 18 months with what we've gone through with COVID. So they're looking at what they've got. So how can we make the most of that? Could we upgrade the sensor on it? Could we upgrade the controller on that? Could we upgrade the software on that? Could we script something? Could we automate that? So we've noticed a very disruptive investment in terms of sensors and retrofit and software on existing machines. So I think Hexagon have unparalleled portfolio. At the bottom there, it started 20 years ago with metrology hardware and software. And that is something that I've been a part of for nearly 15 years now for Hexagon. But as them years have ticked by, in 2014, I noticed Hexagon move into production software, so the CAD/CAM world. And then in 2017, that was a bit of a game-changing moment for us when we started to understand design and engineering. So it really does add a lot of value to the metrology hardware and software aspect. And how does that wrap? So when you've got metrology, when you have design and engineering, and when you've got the production aspect, hopefully for the customer, that gives them quality and productivity, and it gives us the confidence to supply the customer with the best that we can. So I've touched on a little bit of electrification, and I'm glad that has come up a couple of times already on the questions and a couple on the presentations as well. But electrification is a very big talking point for us at the moment, not just in UK manufacturing, but for us as a company. We're trying to understand how we can help, or how we can position ourselves as a company to understand how to make the most of this and how to support the customers that we are. So if you look at a basic car, you got a cabin interior, you got body structure, you got electric, you got the actual electric motor itself, you got the drive chain. I know we're concentrating so much on the battery at the moment and the cell technology, but there's the fuel cells, sorry. But there's so much more when it comes to electrification. So how do I look at that? How do we look at that in terms of mega trends shaping the future for e-mobility for us? So that's automation, the driving task taken over by the vehicle. Are we going to see this? Of course we are. Very interesting, especially with Tesla, especially with taxi bots, all that kind of stuff. It is fascinating to see from a company like Hexagon, to see our involvement in that and some of the projects that we're involved in. Communication, huge. Vehicle exchange data with the city infrastructure with one another as well. Who would have thought that the cars that we drive in today would have that layer of communication, that that technology that we see when we sit into that actual car now. Electrification, just mentioned that before, fuel cell technology, seeing what's happening on that, the race by the OEMs, the likes of the Ford, the General, all them trying to catch up with what Tesla is doing today. I find that fascinating. And sharing as well. I mean, the next generation of people, you know, I know, for example, you know, will you actually purchase a car in the future, or will you share a car or share the ownership of that car? Very interesting seeing that move. So I've picked this as well in terms of a drive line or a drive chain to understand a little bit of smart manufacturing and how Hexagon perhaps can help and to see how all that works together. So if you look at it from a design point of view, so, you know, designing that drivetrain, designing that drive line, from an engineering point of view, from an actual prototyping point of view. So now we've got something physical. Are we going to start manufacturing that? Does that feed back into the design aspect and the engineering, a bit like that digital twin? And then the actual delivery of that, the manufacture of that drivetrain, and the maintenance of that, and that all feeds in with each other from the start to the finish. And then that again is touching a little bit of the design and engineering, the production aspect and the metrology aspect, all coming together and working together. And why I wanted to touch on that is that's why Hexagon have been positioning themselves, acquiring certain companies to be able to provide that for our customer. So I'm going to go back a little bit to basics a little bit here and give you a couple of examples of what we would do manually at this moment in time in metrology, and maybe how we would automate that response. So what is an arm? So a Hexagon arm is a portable measurement arm. It can be used to measure any part, anywhere, regardless of the shape, size, or complexity. An amazing bit of kit, actually, and something that I've seen really develop over the last 10 years, especially from a Hexagon point of view. We weren't even on the pitch in terms of competing with our competitor in this. But one thing I have noticed over the last 4 or 5 years is how good we are now at producing arms, very accurate arms, and the sensor technology on them, and the scanning technology. So what is a laser tracker? Now, this is something that I've personally been using for the last 20 years. I pride myself on the kit that I use, and also the Leica brand and the Leica laser trackers. I was using these for nearly 10 years at Airbus. So laser trackers are portable measurement systems able to accurately measure 3D points in any environment. So instead of taking the component to what you need, so instead of taking the component to your measurement device, just lost my sign there. Let me just take that on there. So instead of taking your component, what you need to measure, to your measurement device, we actually take the measurement device to what you need to measure. So the presentation we had before, you know, fascinating conversations there of how would you measure something of such quite a large component of that. You know, how would you verify it to the CAD? How would you verify it to the nominal? You know, but I would say laser trackers pretty much, you know, is very much a human element. Every example you see on that screen, there's a human or there's an operator operating that laser tracker, and that was the same with the arm there. If you look at the 3 examples there, you've got a human element of that. So we've got a new technology that we released last month, and that technology is a new scanner, and that's nothing new for Hexagon. We've been producing and manufacturing and selling scanners now for decades. But what is quite unique about this scanner is the fact that it has cross-platform potential. So you can actually take the scanner, so an AS1, which is his name, which stands for Absolute Scanner, you can actually take that scanner now from the arm and actually put it onto the actual laser tracker itself. And that is the same scanner. So you don't have to buy 2 scanners. And for me, when you talk about disruptive or future innovations, that is, for me, working at Hexagon for 15 years, that has been something that I've been waiting for, to get an item from one hardware and to put it onto the other. So if you imagine a CMM, if you imagine an arm, or if you imagine a laser tracker, to be able to get a scanner and to remove that from one and to put it onto something else, or to remove it from there and put it onto that one there. So it's cross-platform use, and I have not seen that before from Hexagon. Very, very exciting. And another example of that as well, you know, so you've got the tracker, you've got the arm. You might not need to use the scanner all the time. So you might have, for example, you might have 3-4 laser trackers on site in a factory. Perhaps, for example, at Airbus Broughton, you'd have a fleet of 10 trackers, and instead of having to have 10 scanners, you'd perhaps need 5 scanners, and you would share that scanner. And then you might have a couple of arms back at base in the tool room, perhaps, or in the inspection facility. And this, to me, again, is quite disruptive. So it's okay having it handheld for the arms, and it's okay having it handheld for the laser trackers. But again, you can automate that same scanner, the AS1, the absolute scanner, you can automate that. So we noticed before the end effector on a robot. So you can actually put that scanner, remove the human element, and actually put that onto a robot. And why would you do that? Why would you use a robot to do that? For us, it's been very challenging in terms of automation for us at Hexagon. I've personally noticed quite a low adoption rate of laser trackers being automated, especially our scanning technology. It's been a very hard pitch for our customers to invest in money to do that. Throughput, efficiency, quality. When you are actually using a robot instead of a human, you're actually removing or controlling variables which are not in control, and so the uncertainty comes down. Also, as well, it obviously improves the working environment, but a big negative of automation or automating a process at the moment is expertise for us and integration. So how do you integrate? Who do you get to integrate our sensors onto that robot? So it's that the adoption and change and the training has been a big challenge for us in terms of automation. So again, I just wanted to show you the modular concept of the AS1, which I find, again, fascinating. I've had examples over the years where we've automated, where we've put a scanner onto a robot, and then due to an error in terms of a tool path or a collision, we've basically smashed a 60 to 85K scanner. And once you've hit it, you've kind of wiped out the scanner, and then it's like it's a bit of a game over. It's what have I done moment, you know? Very expensive mistake to have. But one thing we are noticing now from Hexagon is a modulated approach to how we build our components together. So if you did have a smash on a robot, if you did have a slight problem, you could replace the part that was broken. Again, I think this is quite disruptive. So what would you use our technology for? What examples have we done in the past? So example for aerospace, measuring large components such as wings, such as fuselages, such as wingtips. You could use one tracker looking at one robot, or looking at 2 robots, measuring. And I think the difference is, I think when you automate a process, it gives you the flexibility of actually doing that, actually measuring. We're measuring components that we've never measured before, because we can actually do that now from a time point of view. Imagine measuring perhaps a 20-meter wing, for example, on the A380. Measuring something that size, you know, by hand. You probably it's not an impossible task, because we've actually done that. But for measuring small holes, measuring countersinks, measuring waviness on a surface, now this is all possible. So robot calibration and testing is something that we've moved into over the last, I would say, 5 years as well. industry robots, as we know, are repeatable, but from an accuracy point of view, that's maybe why they might be a little bit let down. So calibration can improve the absolute position and accuracy and performance of a robot. If you've got a problem with a robot and you need to replace that robot, a laser tracker is very useful to actually do that. Cell duplication. So if you've got a cell that is working that you know is good, you could duplicate that in other facilities, in other factories. Also, as well, if you could, from a drilling point of view, from a positioning point of view, from a flexible assembly point of view, if you start including a laser tracker and looking at where the actual robot is moving, the accuracy that you achieve is very noticeable. So common problems that we find, especially with a robot on a linear track, is it's never a straight line. I know I've exaggerated this a little bit in terms of showing you curvature and slight linear track behavior, but if you were to include a laser tracker and monitor that robot and the position of that robot on a linear track, you wouldn't have to worry about how straight that actual track was. It does add an extra layer of accuracy into what you need to do. So strategy 1 for us: physical correction and precise alignment for us. Process would be some measurement of a linear track during assembly, and then we would fine tune that based on correction of that track. The limitations of that is much effort to correct the track on adjustable screws. So a lot of manual interventions there, especially for an operator. And then a lot of work effort depending on the track size. So some of these linear tracks are very long in terms of meters, and very large scale. So a lot of temperature distortions as well. So adding a laser tracker, monitoring a robot and its position and where it is in live situ removes the need for that. So integrated 7DOF machine control and feedback for us. So laser tracker used as an inline measurement system. So bottom down view on a kinematic system. So we're looking straight down from the top there, looking at a position of a robot. If the 7DOF, so 6 degrees of freedom, so that 7th degree is us actually monitoring the end effector on that actual robot and guiding and then altering in real time the position of that robot. Control intelligence delegated from robot to external measurement and control system, and reduction of accuracy dependence from the hardware. We've done a lot of work with a lot of research institutes. We're currently doing work with Coventry University, MTC, AMRC, understanding robot accuracy, understanding how we can monitor that accuracy and by using a laser tracker, improving the accuracy of that robot and altering in real time the actual tool path of that robot. It's not always needed, but for example, a good example is of drilling a hole or machining with a robot. Accuracy would be needed. So there's some examples of where we've used our technology with robots. I thought this was really interesting. It's going a little bit away from robots, I know, but we've got a laser tracker there looking at a bottom skin cut section of a wing. So we've actually measured that wing in real time, reflectorless as well. So we're just measuring the surface with the scanner, and then in real time we've actually displayed a color map. So you've got the nominal information, which is your CAD. You've got the actual information, which is what you've retrieved by using the laser tracker. And then you've compared the actual to the nominal. And then we've done a color map. So green is basically in tolerance. Red is actually out of tolerance. So from an operator point of view, or from an engineering point of view, or if you need to position a part in situ, it's an excellent way in real time of actually seeing where your part is. And this is what we've been working with a company called Spotlight AR now, and using projectors to project that color map live onto the surface. So you got an example there of a wing, a bottom skin wing there. You got an example there of a door, and you could also display GD&T information or instructions to the operator of what to do. So if you think about a process, a workflow that an operator has to perform, if you can de-skill that slightly, that process, and show that operator operation instructions live on what they're actually doing, it does add a lot of efficiency and a lot more accuracy as part of that process. And finally, I'm a little bit mindful of the time, and I do talk a little bit, but smart manufacturing for us is something that we've invested a lot in over the last couple of years, and we were trying to work out how best to describe that. How would a factory look in terms of a smart factory, a lights out factory? How would you automate that process? And it starts from the design, the factory operations, the service life, what is actually going on, what is happening in that factory, all these sensors that I've got, in all these Hexagon sensors that they got, and it doesn't have to be a Hexagon asset that we can monitor. So all this information, all this data, we need to be able to view and to use and to start making decisions on. That will improve quality. You've got the manufacturing and assembly, and you've got the engineering. And I just thought that was a very good slide on how best to describe that. And I think that is it. I wish I'd gone a little bit more technical in that. I really do. And apologies if it wasn't as technical as perhaps people were requiring today. But just like to say thank you for the opportunity to present.
Thank you, Tim. That was very, very interesting. Has anyone got any questions they want to pop on the Q&A? Oh, someone's put something in the chat. From Pim. So on questions, I've got one that I've noted down. What challenges do you and your customers face with automation or disruptive technologies?
I personally think it is the biggest one that we're seeing at the moment is time. So the customer has not got the time to perhaps change to a new process or to a new system. They want to try to make it as effortlessly as possible. So I don't know if you find it, Rob, as part of your job. I certainly find it now. We are that lean as companies, where we used to have a dedicated job. Now we've got multiple roles, and what we're seeing now is how can we hold that customer's hand? How can we help them change and to bring in automation as part of what they're doing? And I think they're a little bit scared to do so. Rob, as well. I don't think it's an investment point. I don't think it's an investment problem. I don't think it's a financial issue. But I do think we're lacking a little bit in the UK, Rob, if I can be absolutely honest with you, from an integration point of view. You probably saw the way I stumbled a little bit trying to explain a robot integration for ourselves as well. We've been playing in this area for nearly 10 years, and we invested 4 years ago in a dedicated application engineer on robot integration, and a dedicated salesperson to sell automation. And we gave it 2 years. It didn't quite work for us, Rob, you know, and so we took a step back. But I think now's the time to understand that. But we need to invest. We need to be able to hold that customer's hand, and that's the first thing that they ask us. You know, and we look for integrators basically. You know, and but I think that's the biggest challenge, is integrating the sensors, the skill set needed for robots, and understanding what you've got. That's the biggest challenge that we find.
Yeah, I think I'd agree on some of that. It's particularly when we're trying to encourage some of our clients to introduce more computational fluid dynamics earlier in their design process. it's disruptive and a good thing, and will end up giving them a better product, but they have to change the way they work, and there's a lot of inertia in that.
Yeah, and I think this is why, I think this is why and we're a bit of a believer in the high value manufacturing catapults. So to be able to do this offline and to prove that somewhere else, and then to actually take what you have proven and bring it onto the shop floor. But one thing we're noticing at the moment, the likes of Airbus, Rolls-Royce, Spirit Aerospace, Boeing, a lot of these companies are bringing back their research and development facilities on site and doing it, rather than perhaps, obviously they're collaborating with universities. That will never end. I think that's fantastic work. We're a big believer of that, but we've almost noticed then they're going back to the way they used to do that. If you think of the Wing of Tomorrow project at Airbus, for example, and the new facility they have there at Broughton now, if you think of Spirit, they've got an aerospace innovation center which they've just opened up actually, and that's up at Prestwick. If you think of GKN and their global innovation center they have down at Bristol, I mean, if you'd have rolled the clock back 5 years ago, we wouldn't have been talking about that. So it's understanding how these centres interact with the high value manufacturing model, the catapults within the UK, how the universities can be a part of all that. I know Cranfield work very, very closely with Airbus. We've done a lot of work with Cranfield over the years, but it's how can we make automation easier for our customers? How can we make that easier for UK manufacturing? We're getting there. With the softwares that we use now, the program of the robots, the controllers, the interaction, the cabling, the connections, 5G, it's getting there. But it's how do you connect it all? And I see that being our biggest challenge.
Yeah, very interesting. Right, it's conscious of time for the networking or refreshments break. We're a little bit behind time, so how about we break, people can chat on the various tables, and we'll regroup for Julio to talk at 11:35.
Thanks, Rob. Thank you all.
Okay, thank you.
Thank you.
So if you start talking, I'll just hide myself away.
Okie dokie. Welcome back, everyone. Apologies for the slight delay. We're already 3 minutes behind what I said. We were having a slight technical difficulty with another speaker, but hopefully that will be resolved soon. Next up is Julio Vita from Worth Research, who will hopefully appear on stage any second. Julio is going to be talking about some of the stuff we do at Worth Research, where we've taken technology developed in motorsport and we're now using it in wind engineering, to primarily looking at sustainability improvements. Good morning, Julio. If you want to take over from here.
Thank you, Rob.
Check you can present first.
Yes.
I'll disappear.
Sorry, a bit of a procedure to follow. Can everybody see the presentation? Good.
Yeah.
Brilliant. So I will be talking about what we do at Worth Research and how we interpret the specific topic of climate impact and how this has anything to do with disrupting and future innovation. So in no particular order, I will mention what's disruption and what's innovation for the specific subject of wind engineering. I will be talking about computational fluid dynamics, that is the S in DSM special interest group. So we do simulations for a living, basically. This presentation will be only about buildings, although I will mention also something else we deal with in our company, and then what we envisage the present and the future of wind engineering being at the time. So I think we saw some great presentations to get very technical and very high-tech. So in my presentation, I would like to first explain what is wind engineering, because it's a very specific branch of civil and mechanical engineering and meteorology and atmospheric studies and physics. So I think it's always useful to understand what a wind engineer does. Basically, a wind engineer deals with a fluid, in this case wind, but it could be really any kind of fluid, even inside of a building, and air is moved artificially, hitting a solid body or another fluid, for instance, sometimes. So if the fluid hits another body, it generates a response. So basically all a wind engineer does is calculate that response and designs, improves the aerodynamic or the response of that body. So basically the tools that we use are designed to blow air onto something. And I think this is a really cool thing, and it has a lot of implications, which I'm going to focus on the next slide. So the way of blowing a fluid over an object can be done in several ways. So the first way could be analytical, although for wind engineering we don't really have any tools that allow us for a oversimplification of the problem. So that's not really an option. There are some early calculations that you could do, but normally that's not the main bread and butter of our activities. Most of the industry, the wind engineering industry and the applied aerodynamics, uses physical modeling, which is well regarded. It has a long history, and basically it requires a wind tunnel facility, which is basically a long duct. In order to simulate a building in the wind tunnel needs to be big enough not to have scale issues and all the issues that are deriving basically from not simulating a full-scale building. And basically it is the trusted and go-to instrument to test wind. There is also an alternative that is quite more recent. The first application of computational fluid dynamics are 30 years old, although for buildings we talk more about 10 years old. And it is to numerically solving the problem, the fluid dynamics problem. So solving a set of equations in a way that I will try to explain the way our recipe at Werf Research and how this basically compares to the wind tunnel. Now, the status quo, as I mentioned, is wind tunnel testing. Actually, that's not really true, because CFD, we know, is used effectively since 15 years ago in the aircraft industry. Nowadays, also the vehicle design industry is implementing heavy numerical tools to reduce the design process, to improve the design, to lower costs, and in the end to have better products, because wind tunnel testing has limitations that we know, we trust the tool, and we understand those limitations. Whereas in CFD, there are less results available that make us more careful when we look at the results. But this is actually not a problem. This is the strength of this tool. When I say disrupting, of course, if you have a industrial practice that is all sized and organized to run experimental tests, and then we come as a company with our wealth of experience in numerical studies in an industry that is building built environment that does not really accept numerical testing as yet. This is disrupting to the practices that apply experimental testing. And the way we can innovate, because we believe that CFD is the way to go for the buildings of the future and to tackle climate change, because this presentation is about climate change, is to be as bothering as we can with our competitors, which are, to be honest, they're not really our competitors, because they use a different tool and they are expert in wind tunnel testing. Although they use a very specific and different tool, they are not shy in giving their opinion, saying that CFD should not be used for buildings. Now, this is a problem because there are less CFD practitioners than wind tunnel practitioners in the built environment industry. And a difficulty that we have as a company of providing this service and innovating is to explain that actually there are several kinds of CFD. Our recipe is high resolution, and basically it's as complex as a wind tunnel, and it requires a facility in terms of high-performing computer clusters, and it needs a set of skills that is comparable to the set of skills that is required to run a wind tunnel. And this is very difficult to explain to people who don't know what CFD is. And remember that buildings are mainly the job of civil engineers, and normally fluid dynamics is at their first year of studies, and they don't really go to CFD at all for their field of study. So challenges and in innovating. Now, in our history, as Rob mentioned, we transitioned, we applied CFD. We saw the success in other fields, for instance, motorsport. Then we started transforming this tool to apply it to lorry, saving lorry for haulage. Then designing better supermarket fridges, which is a big part of our business, and developing a product even that I will briefly explain how it works and what it does. What's important is that big data and high resolution simulations, and in general simulating, is key to provide a better product. You can't really design a product without knowing how it will perform in advance before producing it. Of course, a building is not really a product. A building is a prototype. All buildings are different, and you can design 10 buildings having the same plans, but they're actually different entities, possibly built by different companies. So there is a low advance in low tech aspects of buildings that we have to match with our high technology of simulating all aspects of the building physics and behavior for wind, of course. Now, why buildings relate to climate change? I always give this nice phrase to my spectators, if you like. Basically, a thing that is neglected by most of the people I hear speaking about energy consumptions and the energy policy is that around 50% of the energy consumption in the world doesn't come actually from the industrial production or transport. It comes from buildings. So buildings in order to be produced, but also in order to be maintained and operated and to be in service, they require a whole lot of energy that is normally not very controlled because of the fact that the building is a prototype. Okay, we have some, for instance, in the City of London, we have a nice set of guidelines that requires us to do some extra checks. The European Union has some standards that prompt us, if a building is of a certain size, to do some checks, check sustainability and resilience, and the design needs to be conducted in a way that it doesn't consume up to a percentage of the energy required to produce it. But actually, most of the buildings are not large, are not high-end, and they are not designed by, and they're basically the budget to design them is very limited. So this is part of the problem. Buildings are not yet at the same step with the advanced tools that we use. You should have seen a video which is not started, so I don't really know. Apologies. I hope in the next slide we start. So we offer a broad range of services related to buildings. As you see, the level of complexity is not small, although a building could be considered a low level of technology. And all of this is actually doable in CFD. And actually, most of these services cannot be done in the wind tunnel, and CFD is the preferred tool. So how do we deal with a tool that is normally not trusted and and deliver to our clients. So our recipe is called high resolution CFD. So basically CFD, I suppose most of you know, is a tool to solve the Navier-Stokes equations numerically. So you're able to visualize the flow. The caveat to this methodology is that you need a grid, meaning millions of points, meaning millions of calculations, if not billions of calculations. So you need a facility for high resolution CFD. This facility is expensive and it requires experience and expertise to run it. Okay, now the video works. So basically, this is what you get from a simulation. You get either a real-time simulation of the flow, you get statistics from this, and from here you can go to the design. Now, there's a question, of course, of using a virtual tool that is accuracy. Now, in terms of accuracy, the way we find the problem is that the mesh is crucial. So if you have these 4 meshes, for instance, and you want to see what's their impact on the solution, this is a jet, a plume going upwards. Here is what actually happens to the results based on the mesh. So we see that sometimes the definition of CFD does not match with the result. So the coarse mesh CFD and the extra fine mesh CFD are both CFDs. If you look at the coarse mesh, you say, yes, CFD is not a suitable tool, but actually it is a suitable tool if you use an extra fine mesh. So how do we innovate and how do we present this to people who don't have this expertise? So that's one of the things that we must we must deal with on a daily basis to explain to people what we do and that we do trust what we do, to be honest. Now, I mentioned that in the built environment it's not very common to use CFD. Actually, at Werf Research we have been using CFD for a long amount of time. My previous experience is academic. I have 5 years experience in the University of Birmingham, but I joined Werf Research in the past 6 months, and I must say that experts in the built environment know that CFD can be used, and as I was, so I found myself at home immediately at Werf Research and with this philosophy, and I am absolutely honored to work for them because I can tell you there is no other company working in the built environment who has this wealth of experience in CFD specifically. Now let's go talk briefly about my computer just froze. Sorry. Echo. Fantastic. Apologies. Let me try. As I mentioned, there is a bunch of services that we offer. All of these are comparable in terms of the complexity required to the tool. So CFD, as we said, is a highly advanced tool. So one of the first issues we are called to solve is wind microclimate. Now, how does this relate to climate change if this is a comfort issue? So the ability to enjoy the public spaces around buildings. Now, this is directly related to the fact that we built more and we need bigger buildings to support our activities, and also that our lifestyles have become more complex. So we need our environments to be climatized and to be accessible and to have common spaces and to network, and all these activities require basically energy and bigger buildings. So the risk is that wind goes in between the buildings and it becomes unsustainable, and we forget the very reason why we're building, that is enclosing a space where we are protected from the outside climate. So developing and having bigger buildings goes together with climate change, of course, but also with comfort. They're not exchangeable issues. And now we have, you see the level of complexity requires meteorology, requires CADing, requires visualization tools, and then there is the combination with the sun ray tracing. And then we provide what is called comfort criteria to design the design the comfort, because you do design the comfort. You decide where are those spots where you can have an entrance, you can have a seat, etc. 22 Bishop Gate was an important job for us, and we have done, I believe, over 100 simulations to get that sorted. And that's the complexity. So you see all the steps that are required to have a full microclimate assessment for planning. And most of the times planning goes together with wind tunnel testing. So specifically, the City of London asks for both wind tunnel testing and CFD. And from our experience and our large number of jobs, we don't see much difference between the two tools. So you see the maturity of the tool and how it is difficult to present to clients, given the reputation that comes from the fact that CFD is innovative and newer if applied to the built environment. Another picture of a wind tunnel compared to CFD. I'm going to skip this. I'm going to skip this as well. More related to energy, there is also another issue that we're really tasked with, which is the design of ventilation. So natural ventilation was how buildings were designed throughout history before systems were invented, and they were working fine. If we are thinking about the London Parliament, the Houses of Parliament, it didn't require anything else to move the air inside the building other than the heating source. We have lost that culture a bit because now we require testing and quantify the amount of ventilation you can get. CFD is nowadays the only tool that allows you to recover that culture, which is very British in my opinion, and design new buildings which work on natural ventilation only. We have done the Bloomberg Place in London. There was a nice video playing here. We have done also the Apple campus in Cupertino. So you see, it's quite important landmark buildings. But if we manage to convince the planning authority that CFD can be used, because this kind of activities cannot be done in wind tunnel or in any other tools, for instance, in full scale or with analytical methods, this is able to reduce strongly the amount of energy used by a building. If you also compare with our activity, there were some videos here, I'm sorry. If you also compare with our activities of designing better supermarkets, and if you count the amount of supermarkets that there are in the UK, you see that the energy savings that you could get are absolutely massive. And that's where innovation plays a role. So we strongly believe that we are the go-to people to do this. As well as industrial building. I mentioned that in industries, although they use lots of energy, most of this energy is used by the building rather than the production activities most of the times. I was mentioning the air door, but I don't have time. You can ask me questions and I'll show. And structural wind loading is where wind tunnel, basically structural wind loading, you design the structure for wind loading. The wind tunnel is the preferred tool. Wind tunnel is the tool that everybody trusts. If you want, is a low technology tool compared to CFD. And here is a spread of different wind tunnels and how our high resolution CFD compares. So you see the technology is pretty mature, but we need to sell it in a better way. We need to convince stakeholders to take the risk, which is a no risk, but is a new thing. So innovation is sometimes associated to risk. That's why it's so difficult to innovate. And those were some nice videos. And you could also apply CFD with multi-physics problems. So not only solving wind and the effects on a structure. Here you have an example with the two flows interacting, which is rain and wind, but this could go for sun and wind. This could go for, of course, temperature and moisture content, COVID contaminant diffusion, and I mentioned comfort. I hope that I haven't bored you too much, and if you have any questions, I'm here. Thank you.
Thank you very much, Giulio. Does anyone have any questions? Post them in the Q&A. No, I'll just add one. You mentioned briefly at the end there about COVID contamination. Do you want to just say a little bit more about that, because it's well, it's been in the news recently for the last year or two?
Okay, so first I'm just reading the comment from Jerome. Thank you very much. Yeah, I was sure somebody would understand my struggle. So now, of course, if you switch on the television, COVID is everywhere. And what I find flabbergasting really is that everybody interviews virologists and epidemiologists and this kind of health professionals. So they are experts and they know how a virus spreads in the human body, or even statistically how it spreads through the population. However, I've never seen, if only a handful of mention to the fact that the preferred way of transmitting COVID is through air. So you would assume that they would interview a airflow expert or an aerodynamicist, or even a civil engineer knowing how, or a mechanical engineer knowing how ventilation works. And I believe this is a big problem, and this has been one of the main reasons why we have been in lockdown for so long, that we weren't able to convince, as engineers, of course I can't blame virologists because they shouldn't know anything about ventilation. As engineers, we weren't able to convince the politicians that our job is actually to understand how these aerosols, if the virus spreads like an aerosol, spreads indoors and contage people. At Worth Research, we have developed a technique to separate the two ways COVID spreads from the literature. So basically, there is the first phase that is a horizontal, what I call horizontal airflow contagion. So basically, the droplets of saliva, which then has a life depending on the moisture and the temperature and even the velocity of air. Now, that is the most dangerous phase, because if you are standing behind a window and there is a flow of air, this could really reach far distances. And I believe this has made quite a massive impact of the number of contagious people we see. Then there is the second phase, when the saliva droplet ends its life. There is the droplet nuclei, so the so-called aerosol. Now, nobody really knows how this really works for COVID, but we know from other pandemics in Asia and Africa that vertical draft is the way to go. Now, if you have an environment where you have a good horizontal flow and a good vertical flow, this is not really easy to achieve. So this needs to be designed. Again, we have developed this tool, but we don't really see people interested, or if anything, talking about this. So definitely innovating means using a tool you are familiar with, also to respond to the news really, and to the updates. I don't know if it replies.
No, that was very interesting. We've got a question from Sarah Penrose, a chemical engineer and business trainer. Do you have any involvement with CFD in reactors or fluid mixing?
At Worth Research, I don't think I've heard anything. Maybe you can answer this one.
Not in reactors. We've looked at a bit of injection for a piston engine a number of years ago, and oil flow inside a gearbox, both in terms of slosh and pickup and redistribution, but also the gears spinning up. But we haven't specifically done reactors, but we could. It's probably time we move on now. So thank you very much, Giulio.
I will reply to Taf in writing.
Okay.
It's just asking. Thank you, Rob.
And Pim will be bringing up on stage Jerome from Unity, who has got a fascinating and visually pleasing presentation about the use of Unity, which is a gaming graphics engine in all sorts of different new industries. Over to you, Jerome, and you are on screen, so it's working. But we can't hear you. Do you want to try saying something, Jerome?
There we go. Is that working now?
Yeah, perfect. Brilliant.
Awesome. Sorry about that.
That's all right.
Had to reset my settings before. All right. So let me go back to my slides.
Okay,
all right. Thank you, Rob, and thank you for inviting us to present today here at this Disruptive of Future Innovation event. Quite interesting, and I loved the two presentations that I watched beforehand. So making sure that this works. There we go. It's a little slow, but I can see the slide changing. So my name is Jérôme Morgan. I'm a senior technical specialist for industry here at Unity. I'm based in London in the UK. And I've been a Unity developer since 2009 and joined Unity in 2018 as a solution engineer, working with some of the leading industrial customers, leveraging Unity for their product lifecycle. And last year joined a more marketing-focused team as technical specialists. We used to be called evangelists, but now the new title is technical specialist. You have my detail there, my email, my Twitter handle, and a link to my LinkedIn profile. Feel free to ping me if you have any questions after this presentation. So let's see. There seems to be a delay between my slides updating and there we go. So it feels a little bit slow. Right. So at Unity, we believe the world is a better place with more creators in it, right? This philosophy is centered around serving creators and at the breathing heart of our company. It motivates each and every one of us to deliver basically tools, services, and solutions for them to be successful as they create and operate real-time 3D experiences. Hopefully, this is going to switch to my next slide. So here are some numbers that I wanted to share with you today. On a monthly basis, about 5 billion applications made or built with Unity are downloaded. There's over 13,000 projects being created on average every day on the Unity inside the Unity editor. That's well over 4.5 million new projects created in 2020 by our creators. All of the top 10 car manufacturers are using Unity as part of their workflows or product lifecycle, and over 2.7 billion end users consume content through either Unity applications or applications and experiences hosted or leveraging Unity solutions, right? We have a wide net of offering when it comes to games, which is where we originated, right, as a game engine, but also inside what we call the new verticals, which include automotive transport manufacturing, architecture, engineering, construction, and operations, but also media and entertainment. In this presentation, I want to focus on the industrial sort of aspect of the industrial process. Sorry, it's taking a while for my slides to update here. There we go. Thank you. So it's a challenging time if you're a manufacturer, right? You are faced with complex automation production lines. You have to reduce, obviously, your risk, your costs, and your time scale when it comes to developing new processes or bringing new products to market. You have to train a digital native workforce, right, which is coming online and has different assumptions when it comes to training. Also, obviously, training in challenging environments where you cannot take production lines offline in order to train on specific machineries, but also sometimes you may not be able to have access to facilities right now to train a workforce efficiently and safely. There's also a high pressure, fast paced environment. Change is constant, right? There's a lot of disruption between Brexit, for example, with the supply chain, but also COVID and disruptions all throughout the manufacturing process, which requires being a lot more agile, obviously constantly customizing the way we manufacture or handle the product lifecycle and improve on processes as much as possible. This is where real-time solutions and digital twin come into play, right? This allows, in the manufacturing sector, right, virtual commissioning to design, test, and iterate on a solution is critical in order to rapidly evolve, for example, or test, validate ideas, right? It allows you to create complex connected systems, as we saw before with the CFD, for example. Data allows you to bring some of that data inside a real-time environment to see, for example, impact as you make changes. This is being used by some of our customers specifically that are reliant on wind and also fluid dynamics, right? In general, it allows you to connect those systems through either software controller or even hardware controller, right? Connect to data sources and test the human-machine interfaces that you might have to develop for various systems. It also lets you ask the question, what if? What if we do this? What if we try that? Right? It allows you to break things in a virtual environment with little to no cost to the business, but also, helps drive innovation. And as I highlighted, test, validate, and deploy obviously test and validate virtually, and then deploy a cohesive tested solution to the shop floor or to the to drive your process. I'm going to go into some of our customers using Unity right now, and I wanted to touch on Volvo, which is improving collaboration between designers and engineers, right? But also reducing costs, right, and saving money by reducing their reliance on physical prototypes, right? Physical prototypes of vehicles, which are extremely costly and slow to manufacture or create, but also engage car buyers with immersive experiences. So further down the line when it comes to sales and marketing, and accelerate, for example, their autonomous driving development, right, by using Unity as not only a testing ground for some of the data sets, but a source of synthetic data generation to train autonomous algorithms or validate, for example, assumptions, right? Lockheed Martin, since implementing a solution called ChillNet, right, which is a Unity-based application that they developed, Lockheed has seen a tenfold ROI on building products virtually versus physical builds and testing, right? In 2019 alone, they avoided about $10 million in costs, right, with VR-assisted validation, allowing the discovery and resolution of issues much earlier in the development stages, while drastically lowering the risk, right, of products incurring problems or after manufacturing. Right? So all of these can happen digitally, virtually, even before any sort of physical manufacturing has taken place. The company also avoided $500,000 in travel expenses in 2019 and stayed productive, right, throughout the pandemic, or much more productive throughout the pandemic, by having this dissociated network of immersive endpoints where engineers and designers could meet and test and keep validating their solutions without having to travel cross-country or internationally, which was very complicated, or has been very complicated in the past 16 months. Right? Then Toyota. Toyota is using Unity, Microsoft HoloLens, specifically the HoloLens 2, and machine learning to reduce human error during inspection, and reduce the possibility of human error is always present and always in front of mind, right? Even among experts, right? A simple error such as a loose cooling cap or overlooking a poorly fitted, for example, part can lead to it can have dramatic consequences for the vehicle and should be corrected immediately. So relying on Unity as the runtime application on the HoloLens and machine learning, they're able to assist their technicians and engineers and make sure that they don't miss a step, right, which is quite important. In the construction field, Skanska has been doing safety training for their workers in VR, right? So really helping workers be aware of the risks associated with being on a construction site. They are also developing applications for 4D visualization, so see the sequences or the stages of a building construction virtually and being able to better plan, better manage construction sites and construction projects, right? Thank you. Shop Architect is using Unity and a technology that we developed called Reflect to connect their BIM data, the building information model, to the field, right, to the job site. So better communication with key stakeholders, right, and also reduce change orders, construction times, and costs, right. It streamlined the creation of 3D experiences using Unity and Reflect, right, and takes minutes instead of days to optimize large design models, right. Democratize again the access of BIM throughout the life cycle of the building, of the construction of the building, but also throughout the teams and contractors involved in this massive project. As you can see in the image there, the data is actually overlaid on top of the physical site, so you can even pre-visualize in situ what the construction phases are, and also make sure that the physical constructed structures, for example, align as close as possible with the digitally designed ones. Right? So all of these bespoke use cases were either built by our customers, right, built in collaboration with Unity, or built by customers and agencies. But as a whole, because Unity is still very much a game engine at its roots, right, and this is really the majority of the use case for the Unity platform, we have actually architected solutions that help industrial customers get started and get productive a lot faster. That starts with the Unity Industrial Collection, which is specifically tailored for people or for customers using industrial data sets. But we also have a suite of purpose-built products and verified solution partners, which I'm going to be covering in the next few slides. So let's get started. And sorry, there's a bit of a delay between picking and the slide updating, so I want to make sure that we are looking at this thing. There we go. No, it doesn't seem to update, so let me go to presentation maybe. Yes, okay, we're back. So Unity Industrial Collection starts with the Unity editor. This is a customizable, extensible solution. The Unity editor is built, purpose-built for creating content, right, tooling and workflows. It's a extensible using C# as a programming language, so you can actually customize the editor, its workflows, the pipelines that are involved in creating that content to suits you need. And this is really one of the key points that makes Unity such a success. Is it is not a finite solution. It's a solution that evolves with your need and that you can tailor and customize.
I'm actually wondering if at this stage it might be useful to try and bring on Martin Soldert from Symmetry, who is a partner to Unity. Let me see if I can invite Martin onto the stage and see if you can say something. Or Jerome, are you back up and running? We can't hear anything, no. Martin, can we?
Martin is here.
Ah, excellent. We can't see you, but we'll take audio over nothing at all. Do you have anything that you could add to this while Jerome is obviously trying to sort out his issues, maybe? Sorry.
So I'm just trying to see where he is in his presentation because I got it the other day. Okay, but I guess Jerome was the one sharing the screen, right?
Yes.
We can't hear you, Jerome. Okay, but the the overall presentation is really about how we can use the game engines to in the industry to speed up things when it comes to testing and collaboration, and also verification of if you're building this and that machine, you can test it before you actually start building physical parts. And that's important, because as soon as you start to make the physical stuff, then it becomes very expensive. So if we can go in, and I know that the next slide on Jerome's slide deck here was a software called Perspective, which is a partner of Unity, which makes a add-on to the Unity editor where you can actually test your machines in as close as reality as possible, where you can actually hook up your electronics that will run the future machine and have it play out. So you can find problems with the design early, and long before you actually start making physical products. And then there is all of the collaboration stuff. If I'm sitting here in Sweden designing a machine, I can test it, and then I can invite all of you from all over the world to be part of that demo. We don't have to. You don't have to travel to me to look at the machine. We can look at the machine together from a distance, in VR or AR or just on the screen. So the collaboration part is also very, very important to think of. And there were a list before of different add-ons that you could do to be able to do this easier. And Reflect part is one of the things when it comes to pushing data from Revit and Navisworks. And Pixis you can use to import other data formats, most of the other data formats. So it's very versatile and very easy to adapt to what you want it to do.
I've got a question for you, Martin. When you were selecting a partner for this, that you ended up going with Unity, did you explore any of the other game engines like Unreal or CryEngine or what have you?
Yes.
And if so, or if not, do you know what the kind of relative USP is of Unity that made it particularly the right fit for your application?
So from our side, it was a lot of personal because we met quite a lot of people from Unity, and we got really good contacts with them. But also, before we actually became partners with them, we were doing a lot of projects, and we were testing both Unity and Unreal because they're the main engines out there. And when we did that, we kind of stuck on Unity. We liked it better because of the versatility, and nothing bad at all about Unreal. Depending on what you want to do, sometimes I would most likely choose Unreal also. So it's not there is not that much difference between them. The main thing right now with Unity, I think, is their interest in the industry, as they call it, which is anything non-gaming, and that goes both for manufacturing and also for AEC and design and everything. They're putting in a lot of effort into it to grow that part of Unity. And that's good for us because we get good feedback and we have good connections with them.
I suppose that knowing that technology is going to be supported for your industry is breaks down a big barrier to innovation as well, I guess.
Yes, it makes it easier for us to have people to talk to that knows the industry and not only the game in part, and also understands us, what we need and why we need it, and yeah, so that's it. And like Jerome said, this is a tool to create things, just like Inventor or Revit. This is not a solution; it's a tool. If you look at the Unity Reflect, that's more of a end product where you can take your data, push it onto a server, and then you can look at it immediately. It's also there's actually also a plugin for Inventor to push data onto that. So within minutes, depending on your file size actually, you can have a model of a machine or a house in VR or AR on an iPad. So it's very quickly, and these are the things that Unity is pushing right now. It's the ease of use for the industry, not only for the gamers.
Yeah, about 10 years ago or so, we were developing an application that had Unity behind it. That was a visual, basically an augmented reality application that we developed at Worth Research, and we selected Unity because it the packaging was very efficient, and on an iPad 10 or 15 years ago, you've only got a limited amount of computing resource and memory, so the more efficient the packaging up of the data and the models, made it a no-brainer. I guess as time has moved on, the amount of memory available on iPads and iPhones and Android devices these days has just unlocked what you could do with XR or AR on these kind of devices.
Yes, and also now we're actually starting to render in the cloud, so to say, not on your local device, which gives you the same performance everywhere. And this is also one of the good things with Unity. It's that if you've done something in Unity, you can quite easily port it to another device. It's got support for everything when it comes to hardware: iPhones, Androids, HoloLenses, standard VR headsets, and so on. And it feels very comforting to know that if we do this and the customer comes next week and say, hey, can we use this on a HoloLens, then most likely yes, we can. So so that's very good. We actually got a question also in the chat, if we've done any digital twin training apps for military or space applications. As I'm not from Unity, I'm from Symmetry. Symmetry have not made any digital twin training apps for military or space applications, but I'm very sure that someone did that with Unity, because there is a lot of customers doing stuff like this with Unity. So it's totally possible. Then comes the question, what's a digital twin? Do you just want to try it out, or do you actually want to test it? But Unity can handle both. Yeah. And also for training, if you want to set up a submarine with all the controllers and stuff, we can actually make it work within the virtual world, so you can train on everything that you need to train on. And then you can train at home, kind of. As long as you have a VR headset, you can do the training. You don't have to take space in the real submarine or ISS. So that's very, very powerful use cases too with the training.
Geraint, can we hear you? No.
Yes and no. Okay. So okay. Yeah. Any more questions while we're at it? Otherwise, like I said, the end story here is most likely that whatever you want to try or test or play around with your models that you can't do in Inventor or wherever you're designing it, we can bring it into Unity and we can test it. We can verify that it will work. You can show your customers what you're doing, so you can get feedback from your customers very early in the process without having to wait until it's finished when the customer says, no, this is not what we wanted. You can train your staff or your customer staff before the machine exists, so you can save a lot of time. So once it's ready, then people already know how to run it. and you can also train your service personnel. So once you shut down for service, they already know what to do.
I've got one final question before we wrap up. Do you know if there's anyone using Unity to visualize engineering data that's already been generated? So one of the challenges for CFD, particularly the way we do CFD with our very large models, is that we then end up with massive data sets that we have tools to generate streamlines and contour plots and nice visuals, but it would be nice to then have a way to put those into a package that we can then spin around in 3D in front of the end client. So it's about communicating the results to the end client.
Yeah, so we actually did a demo of that a couple of years ago, where we had CFD calculations of a house and the wind, stuff like that, and we visualized it in Unity, and we had people look at it, and you can find, you know, the little problems. You know, on this balcony we will have a lot of leaf and snow because there's a vortex there going around and stuff like that. So yes, that's quite simple. Obviously, it all depends on what kind of data you have to supply with, but most likely there is a way to do this.
Cool.
And I apologize, everyone. I hope you can hear me now.
Yes.
Yeah, we can.
Yeah, I had a complete meltdown. My machine basically froze, so I had to restart and try to rejoin.
No problem.
Terribly sorry about this.
No problem. So, yeah. I don't know how we are time-wise.
We are due to go onto the networking bit now, but I suppose if Jerome's got a final wrap up that he wants to give, then go for it.
Yeah, I mean, I can jump back to some of the solutions we were presenting. I'll share the slides anyway with the audience, but let me go back to my deck, and then hopefully we can make that work. There we go. So I'll switch back to my presentation. So yeah, I was mentioning Unity Robotics Hub. This is an open source project that allows you to get productive with URDF, right? Importing your robot's description files, but also connect to ROS instances. And the latest updates to our NVIDIA PhysX integration makes Unity a really perfect out-of-the-box physics simulations for robotics. Machine learning, AI, and simulation, a lot of this was mentioned in the previous talks. So we are being used to generate synthetic data from the Unity editor, right? Things like pre-annotated segmentation data in order to train neural networks, but also AI Planner, for example, to create decision trees for automated instruction generations, or this decision trees for agents, or smart, or what we call usually NPCs in game. And ML Agent, which is a way to feed basically data to neural network in order to train them on specific tasks where a physics engine is useful, right, to text, for example, in 3D. In XR, I wanted to also mention that Unity supports all of the major XR platforms available on the marketplace, including OpenXR, which is a big focus right now for all the software and hardware vendors across the industry. We are partnering with Vario, who's the de facto industrial VR headset for manufacturing solutions, right? Very high precision, high frequency, and the ability to blend in the virtual with the real, right? So something that, for example, Volvo uses to do some human-machine interface testing or to scenario testing while they are driving vehicles now. Unity Mars, that's a custom-built solution that we propose to the community to really ease the creation of AR applications, right, without having to rely necessarily of being on site, where you can bring basically simulation data like virtual space or digital space, digital twin of space, but also do fuzzy logic creation of rules in order for AR content to be displayed on screen and not having to necessarily push a lot to the device in order to test. So you can bring the testing inside the Unity editor. Interact is a custom-built solution by Light and Shadows for industrial customers. This is really a toolbox to help you get started quickly with process simulation. It does integrate a very high-precision physics engine as part of the package and a visual tool to create your scenarios. PaceLab Weaver is a more traditional immersive training solution with 3 components, right? A creator package to create your scenarios inside Unity, a viewer to enable trainees to access that content, and a management platform to make sure that everyone has completed or is going through the various steps of these immersive trainings. We have a whole ton of webinars, which we do every month, myself and my colleagues, available for you to view on specific topics, so industrial topics, but also product lifecycle things, immersive and machine learning. All of those topics are being covered through those webinars. So, and I have some resources for you, which will be in the slides that we will share after this event, right? And that's me. Ping me on LinkedIn if you have any questions. And again, apologies for the technical difficulties.
Thank you, Jerome. I think it was worth firing through that because there is some really interesting stuff that you added at the end there. So I've already made a note of your LinkedIn and Twitter profiles, so I'll be in touch soon.
They'll be in the slides for everyone to access.
Brilliant. Thank you very much. So I think there's time now to slide into the networking. So people feel free to chat amongst your tables if you've got an extra 15 minutes to hang around before the event closes.
Right. So. Right, thank you very much, Rob. So right at the end, we managed to get Martin's camera to work as well. We apologize for the tech issues. I have no idea what's going on. Obviously, we'll do what we can to make sure that this doesn't happen in the future. But yeah, apologies for all of this. But you know, as per usual, we will be emailing everybody the slides, and we'll also share the contact details of the speakers with everybody. So there is the ability to follow up with Jerome afterwards. And obviously we can only apologize, and you'll get a recording of it as well. We might edit out all the stuff when it wasn't working if we can.
that'd be great. I can re-record after if you want. Well,
let's have a chat about that, Jerome, and see what we can do. But we'll definitely make sure that we hook everybody up and get things sorted. So what I would like to do is just sort of thank all the speakers, and thank you very much, Rob, for comparing today. But thank you, Jerome, thank you, Martin, and thank you to all the other speakers earlier as well. As I mentioned in the text, in 2 weeks' time, we'll have another special intergroup event all about the factories of the future. So I know that Jerome has touched upon this, and I know that Tim Gears touched upon that in his presentations as well. So in 2 weeks' time, we'll have an event dedicated around that, which should be very interesting. And of course, if you want to attend, as per usual, it's free for STC members, and non-members would need to pay. But obviously, Jerome, if you were interested, then I'm sure we could invite you in as a guest. So you know, please do join. Please have a look at the website, silverstontechnologycluster.com for future events and things like that. So yeah, great place to keep posted there. And hopefully we'll see you again at a future one. So please enjoy the networking now, and hopefully we'll see you at a future again. And thank you all very much for joining us. Thank you very much. Bye-bye.
Thank you.
Thank you.